Each year, more than 30 million tons of fiber are produced worldwide. Sisal stands among the most widely used natural fibers on the planet, while premium lotus fiber exists as a symbol of rarity and refinement. So how have humans learned to transform these natural materials into such intricate fibers? The journey begins in vast sisal fields where agave plants are cultivated for years under harsh sun and wind. Once mature, their long, thick leaves are harvested by hand and sent to processing facilities, where they pass through precise and carefully controlled stages to become one of the most durable natural fibers in the world. Alongside this, we also explore a very different transformation: how discarded lotus stems are reborn as rare, luxurious textiles, deeply rooted in traditional craftsmanship and cultural heritage, a refined pursuit for those who value natural exclusivity. Now, join Agriculture Insight as we step into a journey where sisal and lotus silk converge, revealing a unique intersection of agriculture, craftsmanship, and sustainable values. Sisal is primarily cultivated in tropical and subtropical regions, with over 90% of global sisal production coming from Africa and South America. Throughout the 20th century, sisal played a significant role in international trade and was often referred to as green gold, at times serving as a major source of national income for countries such as Tanzania, Kenya, and Brazil. Sisal fiber is one of the most durable natural fibers ever used by humans. Before the advent of nylon, sisal was known as the king of ropes, widely used on ships around the world. With its high resistance to abrasion, exceptional tensile strength, and the ability to biodegrade 100%, sisal remains highly relevant today. And looking ahead, sisal is increasingly viewed as a natural alternative to synthetic plastics, helping shape the future of the green economy and sustainable materials. At the opposite end of the spectrum lies lotus fiber. Unlike sisal, which is produced in hundreds of thousands of tons each year, lotus silk exists in extremely limited quantities, as every strand must be hand-extracted from fresh lotus stems. To produce a single lotus silk scarf, between 7,000 and 10,000 lotus stems are required, and today only a few countries, including Myanmar, Vietnam, and India, still preserve this technique. This rarity is what gives lotus silk its value, often priced many times higher than traditional silk, and elevates it as a symbol of refined craftsmanship and cultural heritage. Now, let us explore one of the world's leading sisal-producing countries. In northern Tanzania, around the regions of Tanga and Morogoro, where rainfall lasts for only 3 to 4 months a year, sisal has not merely survived, but has dominated the agricultural landscape for more than a century. Sisal is typically planted at the beginning of the rainy season in March on gently sloping land where water does not stagnate, yet retains enough moisture for young plants to establish themselves. Seedlings are planted directly into the soil, spaced at approximately 1 meter apart, allowing their long, thick leaves to develop to full capacity. During the first 2 to 3 years, sisal requires very little intensive care. Thanks to a root system that penetrates several meters deep and a natural water storage mechanism within its leaves, the plant can thrive with annual rainfall of around 700 millimeters, significantly lower than that required by most industrial crops. It is precisely this paradox, minimal care combined with long-term productivity, that makes sisal an ideal crop for semi-arid agricultural regions. Have you ever noticed how sisal looks remarkably similar to a plant commonly used to make spirits? In fact, sisal belongs to the same agave family as the plants used to produce tequila and mezcal. However, while agave grown for spirits is cultivated to harvest the sugar-rich core at its center, sisal follows an entirely different path. It is grown to extract fiber from its leaves. This fundamental difference shapes every aspect of how sisal is cultivated and harvested. After approximately 3 years of growth, sisal enters its harvesting phase. The plant is not cut down. Instead, it is harvested repeatedly in cycles, a process that can continue for nearly 10 years. During each harvest, workers cut only the outer, mature leaves, where fiber concentration is at its highest. The central core and young inner leaves are left intact, allowing the plant to continue growing. Sisal leaves are cut close to the base using specialized knives. A harvest-ready leaf is typically over 1 meter long, thick and rigid, and heavy with moisture, requiring a firm, decisive cut to avoid damaging the fibers inside. Over its lifetime, a single sisal plant can produce more than 200 leaves, though only a portion is taken during each harvest to prevent exhausting the plant. Once cut, the leaves are laid out directly in the field, where overly young or damaged leaves are removed. Leaves that meet quality standards are then bundled uniformly, prepared for the next stage of the production chain. On average, a single worker can harvest more than 1 ton of sisal leaves per day. And on large plantations, total daily harvests can reach tens of tons. When sisal leaves enter the factory, the fiber extraction process begins immediately and runs continuously. The leaves are placed parallel on a conveyor belt, with their tips directed toward a set of pressing rollers that use mechanical force to keep them straight and stable. The conveyor then feeds the leaves into the decortication machine, where high-speed rotating drums crush the leaf pulp and separate the long fibers inside. The pulp and plant juice are expelled at the decortication chamber, while the raw fibers continue forward, retaining their full length. A standard production line can process 20 tons of leaves per hour, yet the output is highly selective. Only about 4% of the leaf's weight becomes usable fiber. The raw fibers then pass through a continuous washing system to remove sap and plant residues, before undergoing preliminary combing to separate and straighten the strands. Within just a few minutes, a fresh green leaf is transformed into raw fibers, ready for the next stages of processing. After washing and preliminary combing, sisal fibers enter the drying stage, a critical step that determines both color and durability. The fibers are spread out or hung evenly on drying racks, ensuring they do not overlap so moisture can evaporate uniformly. In major production regions such as Tanzania and Brazil, sisal is typically sun-dried, where ambient temperatures average around 30 to 35 degrees Celsius. The drying process usually lasts 2 to 3 days, until the moisture content of the fibers drops below 12%, a safe level for storage and further processing. If drying is insufficient, the fibers may darken, lose strength, and become more susceptible to mold. After drying to the required standard, sisal fibers are collected directly at the drying yard, the moment when the fiber's final form first becomes clearly visible. The fibers are removed from the racks and carefully recombed to eliminate short strands, sand, and remaining impurities. They are then graded by length, color, and uniformity. From over 1 ton of fresh leaves, only around 40 kilograms of usable fiber remain, bundled into 20 to 25 kilogram bales. This is the critical stage where raw mass is refined into true value. After being delivered to the factory, sisal fibers are fed into an industrial rotary drum combing machine to clean and even out the fibers. Inside the machine, steel rollers fitted with metal teeth rotate continuously at a speed of approximately 400 revolutions per minute, pulling and aligning the fibers in a fixed direction. This process straightens the fibers, separates tangled bundles, and removes short fibers and residual debris. The spacing between the rollers is precisely calibrated to just a few millimeters, sufficient to clean the fibers thoroughly without breaking the long strands. Immediately after combing, the sisal fibers are transferred directly to a hydraulic baling press. Here, the fibers are compressed into standard bales weighing approximately 25 kilograms, reducing volume and stabilizing their shape. The baling stage marks the end of fiber processing within the factory, transforming loose sisal fibers into a complete raw material unit ready for the next stage of spinning. At the spinning mill, sisal fiber is not fed directly into the twisting process. The first step is fiber alignment. Bundles of fiber are separated, stretched, and arranged parallel along a single axis. This step eliminates the natural misalignment of plant fibers, the primary cause of fiber breakage if twisting begins too early. Once the fibers are aligned in the same direction, primary twisting begins. At this stage, the fibers are lightly twisted at a density of around 100 twists per meter, just enough to form a stable single yarn. The goal is not strength, but to prevent the fiber from separating during further processing. Next, the single yarns are plied and subjected to secondary twisting. Depending on the intended application, sisal may be spun into 2-ply or 3-ply yarns. Increased twist density locks the fibers tightly together, creating a structure capable of bearing load and resisting abrasion. Even a small deviation in twist level can reduce the fiber's service life in real-world use by up to 40%. At the end of the spinning process, sisal yarn is twist set and strength tested, then graded and sent on to subsequent stages, most commonly rope making. And now, sisal yarn enters the rope-making stage, where a single strand is transformed into a fully load-bearing structure. The process begins with strand assembling. Multiple spun yarns are fed in parallel into the machine and held under controlled tension before moving into the next twisting phase. This is followed by cable twisting. The strands are twisted in the opposite direction of the original spin, balancing internal forces and preventing the rope from unwinding under load. Depending on the design, sisal ropes typically consist of 3 strands, each made up of dozens of finer yarns. This multi-layered structure allows the rope to distribute stress evenly and improves resistance to abrasion during use. Once the required twist is achieved, the rope is set and continuously straightened over lengths of up to 200 meters in a single production run. Even minor deviations during twisting can create localized weak points. For this reason, finished ropes undergo load testing with tensile strength capable of exceeding 1 ton before being cut, coiled, and packaged. At this point, sisal completes its journey from a plant-based fiber to a reliable load-bearing tool used across everyday life and industry. The journey of lotus fiber follows a completely different path, more meticulous, more labor-intensive, and far more delicate. Lotus stems are typically harvested between May and August, when the plant is at its peak growth and the fiber content inside the stem is at its optimal condition. The ideal time for harvesting is early in the morning, when the stems are still fresh, rich in natural sap, and have not yet been dried by the sun. If harvested at midday or in the afternoon, the fibers inside quickly lose their elasticity, making them extremely difficult to extract. After harvesting, the lotus stems are washed thoroughly before any further processing begins, in order to remove mud and impurities, and to keep the stems fresh so the fibers are not damaged. The extraction of lotus fiber must be carried out within 6 hours after harvesting, while the lotus stems are still fresh and rich in natural sap. First, the stems are cut into short sections of about 20 centimeters, a length suitable for hand processing. Each section is then gently broken open, exposing the fine fibers hidden inside the stem. From each section, the artisan typically pulls out around 10 extremely delicate fibers, almost transparent and very easy to break. These fibers are too short to be used individually, so they are joined together by hand, lightly twisted between the fingertips to form a continuous thread. Throughout the process, the fibers are kept slightly damp with water, which helps maintain flexibility and prevents breakage. The entire operation is slow and entirely manual. On average, a skilled worker can extract about 200 meters of lotus fiber in a single day. If the stems dry out or the movements become too forceful, the fibers quickly become unusable. After spinning is completed, the lotus fiber enters the winding stage, the final step before weaving. At this stage, the fiber is guided through a winding machine to control both tension and direction. The machine keeps the fiber under just enough tension, preventing sagging, misalignment, or overlapping as it is wound. The winding process moves very slowly, as lotus fiber is extremely fine and fragile. Any sudden increase in tension can cause the fiber to break at its weakest point. During a stable run, the fiber can be wound continuously into a spool of approximately 150 meters, sufficient for use as warp yarn on a traditional loom. If the fiber is unevenly distributed, or the spool becomes misaligned, the entire roll cannot be used for weaving. For this reason, the artisan must constantly observe the process, adjusting the hand crank and machine speed. It is at this stage that loose lotus fibers are transformed into ordered spools, ready to enter the demanding process of lotus silk weaving. When the lotus yarn spools are ready, the process of weaving a lotus silk scarf begins with loom setup. The lotus yarn is stretched as warp threads on a traditional hand loom, one strand at a time, with tension carefully calibrated to keep the fabric surface even. If even a single thread is misaligned, the warp can break during weaving. During weaving, the artisan opens the heddles to separate the warp threads, passes the weft yarn through the opening, and then beats very gently to secure each row. Every movement is slow and deliberate, as lotus fiber is extremely fine and brittle. In a single working day, the weaver may need to stop hundreds of times to repair broken warp threads, something that rarely occurs when weaving silk from silkworms. Each repair requires precise tension, otherwise the fabric surface will be flawed. At this pace, completing one lotus silk scarf typically takes around 7 consecutive days, with less than 1 meter of fabric woven per day. This slow, high-risk process, entirely dependent on skilled craftsmanship, is what drives the price of a lotus silk scarf to between $300 and over $1,000 USD, making it a textile that is nearly impossible to mass produce. Before each harvest, many farmers in South America still choose to treat their sugarcane fields with fire, clearing dry leaves, driving away insects, and cleaning the stalks. Although burning sugarcane allows for faster harvesting, the environmental consequences cannot be overlooked. In Thailand and Brazil, the smoke from burning creates black smog, a dark haze stretching for dozens of kilometers, paralyzing traffic and forcing schools to close. More dangerously, just a single spark caught by strong winds is enough to consume an entire field. Many regions are forced to restrict burning to after 5 p.m., under strict supervision, to prevent the sugarcane fields from turning into a sea of fire. Due to these consequences, many countries are gradually restricting sugarcane burning and shifting toward a more environmentally friendly solution: fresh harvesting with modern machinery. In modern sugarcane harvesting, the first step is cutting the stalks close to the ground using a specialized blade assembly. Thanks to intelligent sensor systems, the machine can automatically adjust cutting depth, travel speed, and leaf blowing direction, ensuring the roots remain unharmed while keeping the stalks clean and low in impurities, a crucial factor for maximizing extraction efficiency at the mill. When cut correctly, sugarcane can regenerate from the same root for 3 to 5 consecutive seasons, helping farmers significantly reduce replanting costs. Right after cutting, the cane moves into the central processing system. Leaves are separated or chopped and returned to the field, while the stalks are uniformly segmented and transferred onto a conveyor system that loads them onto collection trailers. Notably, the harvester is also equipped with an automated hydraulic arm, allowing it to gather and unload cane into the trailer with precision, all without stopping the machine. optimizing the entire harvesting process right in the field. After harvest, the sugar cane is transported to the mill as quickly as possible by truck or train, because within just 24 hours its sugar content can drop by up to 15% due to dehydration and natural enzymatic breakdown. At modern sugar mills, thousands of tons of cane are received each day and moved into the pre-processing area. All incoming cane is accumulated on large storage yards or continuous conveyor systems. When processing begins, the cane is fed into intake hoppers and directed toward the primary handling equipment. Before pressing, the cane passes through a high-pressure water spray system that thoroughly removes dust, soil, and any surface impurities. Tiny grains of sand, seemingly harmless, can wear down the steel rollers and damage an entire multi-million-dollar mechanical line. The wash water is then recovered and treated in a closed-loop system, because even a small amount of bacterial contamination can cause the juice to ferment prematurely, ruining the entire batch of sugar from the very first stage. This is why the washing step, though simple in appearance, plays a critical role in the whole sugar production process. After the cleaning stage, the freshly cut cane is fed into the shredding system. Here, high-speed rotating knives continuously cut, slice, and tear open the tough outer rind while breaking down the inner fiber structure. This process softens the cane, increases its surface area, and exposes the sugar-bearing fibers within. By loosening the material and opening the cell walls, the shredder ensures that the downstream crushing mills can extract juice far more efficiently and with maximum yield. Next, the entire stream of material moves into massive, multi-roller crushing mills, equipped with a multi-stage roller assembly operating on a progressive compression mechanism under immense pressure. From here, a curious separation begins. The sweet cane juice becomes the next raw material for producing sugar, the white gold that sustains an entire industry. What remains, dry, fibrous, and seemingly lifeless, is the bagasse. Yet with modern technology and a new mindset, these discarded fibers are now collected and reborn, beginning a different journey, where waste is no longer the end of the story. Right after the juice is fully extracted at the sugar mill, thousands of tons of dry bagasse are gathered into massive outdoor piles. In countries where the sugar industry operates year-round, these bagasse hills can reach 5 to 6 meters in height and stretch across hundreds of square meters. The drying process may seem simple, but it is an extremely critical step. Excess moisture, if not removed properly, can cause the bagasse to rot, develop mold, or even ferment, leading to losses of tens of thousands of dollars. With natural sunlight and good ventilation, this drying period can last from several hours to a few days, depending on the weather and the thickness of the pile. Once dried, the bagasse is collected using loaders or conveyor systems and transferred onto specialized trucks. From there, it is transported to recycling facilities or biomass processing plants, where the material is revived and transformed into higher-value green products. At the recycling plant, the bagasse is received and carried directly inside through a continuous conveyor system. The first step, and one of the most critical, is cleaning the material. Here, the bagasse passes through a high-pressure water spray system to remove soil, sand, shredded cane fragments, and any remaining sugars clinging to the fibers. After washing, the material is mechanically dewatered or lightly dried to reduce its moisture content, creating ideal conditions for the subsequent grinding stage. The milled bagasse fibers are heated to 130 to 180 degrees Celsius, then blended with a small amount of natural starch or recycled pulp to improve flexibility and prevent cracking. Even in tiny quantities, these additives are key to turning the fibers into a strong, mold-ready biomaterial. After the refining process, the semi-liquid bagasse mixture is fed into specialized metal molds, preheated to 160 to 200 degrees Celsius. These molds are engineered with absolute precision for each product shape, from spoons and food containers to cups. When the mold closes, high pressure compresses the mixture into its final form, creating a solid structure through heat and compression alone, without the need for any chemical adhesives. When the hot pressing stage is complete, the product has taken shape but remains soft and firmly attached to the mold. It is sprayed with high-pressure cold water to cool it rapidly and assist with demolding. The entire mold set is then immersed in a vibrating water bath, where swirling currents cool the product completely and allow it to release smoothly from the mold without cracking or warping. After being dried to stabilize its moisture content and increase surface rigidity, the product becomes fully formed, sturdy, and ready for the trimming stage. At this stage, the excess edges formed during hot pressing are cleanly removed using specialized trimming blades. These high-speed cutters are calibrated for each mold design to ensure sharp, precise cuts without distorting the product's structure. The edges are then smoothed either by automated machinery or by skilled workers, eliminating any remaining fiber burrs, small details that can affect handling comfort and overall safety. In more advanced facilities, this entire process is fully automated through robotic systems. Integrated cameras and optical sensors continuously scan the product's surface, detecting even the slightest irregularities along the outline. The robot then adjusts cutting force, angle, and speed in real time, creating perfectly consistent edges that manual trimming could rarely achieve. Skipping this step would leave sharp or uneven edges on the product, compromising not only its visual quality but also its safety. Such imperfections can tear packaging during transport, scratch the user's hands, or create discomfort when the product comes into direct contact with food. For these reasons, edge trimming is an indispensable stage to ensure the final product meets rigorous standards of quality, safety, and user experience. Finally, the surface of each product is coated with a bio-based waterproof layer made from plant waxes or natural polymers. This ultra-thin coating allows bagasse items to withstand high temperatures, oily foods, and even liquids without absorbing moisture, softening, or deforming, an advantage conventional paper products simply cannot offer. Next, every plate, spoon, or container passes through a quality control system before being counted, sorted, and packaged by workers using recycled paper or cardboard to minimize environmental impact. From the production line, these items, once nothing more than agricultural waste, are shipped to supermarkets, restaurants, and food outlets around the world, where they replace single-use plastics with a solution that is sustainable, safe, and emblematic of modern green innovation. Have you ever wondered why products made from bagasse feel as sturdy as plastic while still being environmentally friendly? The secret lies in the way cellulose fibers naturally bond with one another under high heat and pressure, forming a kind of bioadhesive created right inside the mold. In theory, products made from bagasse can fully biodegrade in just 60 to 90 days, an impressive figure compared to traditional plastics, which can take 500 to 1,000 years to disappear from nature. But the reality is more complex. This rapid biodegradation occurs only under industrial composting conditions, where moisture, temperature, and microorganisms are carefully controlled. Cotton plants are like the superstars of the agricultural world. They grow their own outfits. These shrubs produce fluffy white balls of fiber that not only look soft and cuddly, but also make everything from your favorite jeans to that shirt you've been wearing since college. Native to warm regions, cotton thrives in sunny fields, soaking up the heat like it's on a permanent vacation. With roots that dig deep into the soil and leaves that fan out like tiny umbrellas, the cotton plant is as hardworking as it is stylish. Farmers plant cotton seeds in spring, spacing them out like disciplined little soldiers. Over the next 6 months, the plants grow into knee-high bushes, their leaves soaking in sunlight like mini solar panels. With regular irrigation, fertilization, and pest control, the plants mature and begin to produce their prized fluffy bolls. When the fields start to look like they've been dusted with snow, it's harvest time. In its early days, the cotton industry was a game changer, albeit one built on hard labor and rudimentary tools. Long before mechanical harvesters roared across fields, cotton was painstakingly picked by hand, often by enslaved workers in the southern United States. The invention of the cotton gin by Eli Whitney in 1793 marked a pivotal moment, turning cotton into a profitable crop almost overnight. Globally, the demand for cotton skyrocketed during the Industrial Revolution, with textile mills in Britain and beyond spinning the fibers into fabric, cementing cotton's role as the lifeblood of the early modern economy. From humble, labor-intensive beginnings, the cotton industry laid the foundation for industrialization and global trade, proving that even the fluffiest of plants can shape history. Harvesting cotton in the United States isn't just a farming activity. It's a spectacle of modern technology, skill, and logistical coordination. With millions of acres of cotton fields spread across states like Texas, Georgia, and Mississippi, farmers rely on both manual labor and cutting-edge machinery to get the job done. Before mechanical harvesters became the norm, cotton was harvested entirely by hand, a painstaking process that required workers to pluck each boll individually. Even today, some small-scale or specialty cotton farms use manual harvesting methods. Why? Because hand-picking ensures minimal damage to the fibers, producing higher-quality cotton. Imagine walking through acres of fields under the hot sun, filling sack after sack with fluffy bolls. It's back-breaking work, but the precision is unmatched. Hand-picked cotton is cleaner, with fewer leaves and stems mixed in, which means less cleaning during processing. While it's not common in the US anymore, manual harvesting remains a critical method in many parts of the world. For large-scale cotton farms, mechanical harvesters are the heroes of the day. These machines are like the transformers of agriculture, powerful, efficient, and a little intimidating. In the US, farmers primarily use 2 types of harvesters: cotton pickers and cotton strippers. Cotton pickers. These machines are designed to be gentle yet efficient, like a farmer's version of a robotic masseuse. They use rotating spindles to carefully pluck the cotton fibers from the plant without disturbing the rest of the bush. Cotton pickers are ideal for fields where plants are uniformly spaced and bolls are ripe. The result? Cleaner cotton and less debris to deal with later. Cotton strippers. For fields with uneven plant heights or late-season harvesting, cotton strippers take over. These machines are less selective, pulling in not just the cotton bolls but also leaves, stems, and other plant material. The cotton is cleaned later during processing, but this method is faster and more efficient for fields that need a quick sweep before the season ends. The adoption of modern machinery in cotton harvesting has revolutionized the industry, offering efficiency, cost savings, and improved quality. Machines like cotton pickers and strippers significantly reduce the time and labor required to harvest large fields, allowing farmers to manage thousands of acres quickly and effectively. This speed is especially crucial during peak harvest seasons, when delays could lead to crop damage from weather changes. Additionally, high-tech harvesters are designed to minimize cotton waste and ensure cleaner bolls, reducing the need for extensive processing later. Advanced features, such as GPS and precision farming technology, enable farmers to optimize harvesting patterns, saving fuel and lowering overall costs. Beyond efficiency, the use of machinery also addresses labor shortages, a common challenge in agriculture. Moreover, modern equipment reduces physical strain on workers, making cotton farming more sustainable and scalable for the future. Once the cotton is harvested, it's compressed into giant bales weighing about 500 pounds each. These bales are wrapped in weather-resistant coverings and tagged with unique identifiers. This step is crucial for tracking the cotton's journey from the farm to the gin. Imagine a giant marshmallow being tagged and shipped. That's basically what these bales look like. The bales are then transported to nearby cotton gins, where the next phase of the cotton's transformation begins. The cotton gin is where the real magic happens. This ingenious machine, invented by Eli Whitney in 1793, revolutionized the cotton industry by automating the tedious process of separating fibers from seeds. Modern cotton gins are technological marvels, capable of processing thousands of pounds of cotton per hour. When the cotton bales arrive at the gin, they're unwrapped and fed into the gin's machinery. The cotton is fluffed and loosened to prepare it for the separation process. This step removes large clumps and ensures that the fibers are evenly spread for efficient processing. The ginning process involves separating the cotton fibers, known as lint, from the seeds and other debris. High-speed rollers or saw blades gently tease the fibers away, leaving the seeds intact. These seeds are collected for further use, often being pressed into cottonseed oil or sold as feed for livestock. The lint, now free of seeds, is cleaned further to remove any remaining dirt, stems, or leaves. This cleaning ensures that the cotton is as pure and soft as possible before moving on to the next stage. Once cleaned, the cotton lint is compressed into dense bales weighing about 480 pounds each. These bales are wrapped, labeled, and shipped to textile mills, where they'll be spun into thread and woven into fabric. Each bale is tracked to ensure quality control and traceability, making sure the cotton's journey is as smooth as its fibers. At the textile mill, the cotton fibers are carded, which means they're brushed into long, thin strands. These strands are then spun into thread using high-speed spinning machines. The thread can be dyed, woven, or knitted into fabrics for clothing, home goods, and even industrial uses. The transformation from fluffy field fibers to finished fabric is nothing short of extraordinary. Starting as fluffy bolls in the field, cotton is harvested, cleaned, and spun into threads that weave the fabric of everyday life. These threads are dyed, shaped, and stitched into everything from soft t-shirts to durable jeans, cozy sheets, and even medical supplies. Along the way, cotton fibers undergo transformations that highlight their versatility and strength. By the time it reaches store shelves, cotton has traveled from farm to factory, carrying with it the effort of countless hands and the innovation of modern technology. Cotton is more than just a crop. It's a cornerstone of the U.S. agricultural economy. It contributes billions of dollars annually and supports hundreds of thousands of jobs, from farmers and ginners to textile workers and exporters. The U.S. is one of the world's largest exporters of cotton, supplying high-quality fibers to countries across the globe. Cotton has been woven into the fabric of American life, literally and figuratively. It's the material behind iconic blue jeans, soft t-shirts, and cozy bed sheets. Historically, it played a pivotal role in shaping the U.S. economy and society, particularly during the Industrial Revolution. Today, it continues to symbolize comfort, resilience, and sustainability. From the sun-drenched fields of the American South to the high-tech gins and textile mills, the journey of 3.6 million tons of cotton is a testament to human ingenuity, dedication, and the enduring appeal of this fluffy crop. Whether it's a soft t-shirt, a sturdy pair of jeans, or even a dollar bill, cotton touches every corner of our lives. So the next time you wrap yourself in a cozy cotton blanket or slip into your favorite shirt, take a moment to appreciate the journey of those fibers. Behind every thread is a story of hard work, innovation, and a little bit of fluff.